Hello, everyone. Welcome to this session. In this session, we have two papers to discuss. The first paper is from Miguel. He's from the Department of Computing Systems at the University of the Castilla-Mancha from Spain. So his paper will be discussing QoS provision for BXI3-based interconnection networks. So Miguel, please start. You have 15 minutes for presentation and 5 minutes for Q&A. Thank you.
Okay, thank you. Well, first of all, I want to describe the context for our project, and we want to take a look at our proposal for how to implement the quality of service for BXI3. Then we want to evaluate how it performs against the default round-robin scheduling in the network. And we want to end with the outcomes and how our work could be further expanded and improved upon. So out of our heads, we can think about several applications that make extensive use of parallelism and distributed computing, and they are more than suitable for HPC environments. What happens in these platforms is that no application is using all this system at the same time. So they have to share their resources and try not to compete too much so that they do not step onto each other, let's say. So that's why we need the service level agreements, and we need to ensure the compliance. Moreover, some applications, because of their requirements, may have different service level agreements, and we have to make room for all of them. So, as I said, the access to shared resources must be fair. Everyone needs to eventually have access to those resources, but still be compliant with SLAs via arbitration or scheduling, and that's what the system needs to do. So should this not happen, it will produce degradation on applications, and we want to avoid that. Okay, regarding the network side, VXI from Atos, now evident, is already present in some top 500 supercomputers as of June 2024. And it is targeting the post-exascale era, or willing to go to 400 gigabits per second and over 500,000 nodes. So to tackle this issue, they have switched to an Ethernet-based, and they will use the combined input-output queue switch architecture and supporting variable packet size. Our work is, as far as we know, the first proposal to bring this quality to BXI3 for now. So what is quality of service? What is the basis of quality of service? It is classifying and splitting traffic so that the treatment and the access to share resources is differentiated for several different applications. This is already present via differentiated services in other commercial and well-established technologies such as InfiniBand, Ethernet, or Intel's OmniPath. And it can be used. It is the basis to provide quality of service, focusing on bandwidth assignment and latency reduction, especially. So when we get these applications requirements, which are tied to an SLA, and through arbitrations, we get the compliance to those SLAs. Well, we propose to bring that quality of service is to have packet scheduling, and we have decided on arbitration tables to schedule the packet transmission. They store a weight for each service level, and that is used to determine the allocated bandwidth for each of them. The weights are internally translated into units, such as flits or bytes, in the end, information units, to determine how, when arbiters should choose to pick packets should grant transmission to packets from one service level or another. What ports on the network need to do is to know which service level is, let's say, preferred in that moment, and for how long. So if you have when terms are what we call quantum, derived from the aforementioned units, and if you run out of quantum, the turn is switched to the next service level. So let's say, for example, we have a table with 4 weights, 4, 2, 1, 1. that can be translated to a quantum, and that is indeed, if we look to the last column, a resultant bandwidth. Okay, so what happens in the scenario we have just described? If we lay out terms like that, yes, we do get the desired bandwidth allocation. And if we measure the kind of the traffic that, or the bytes that have to be sent from other service levels until two, let's say, turns from the same service level, we can see that that is kind of a distance, and that distance is very similar among different service levels, and that causes a problem because the longer the distance, the greater the latency is. So to tackle this, we want to reduce the turns to a smaller quantum, but we want to select top priority entries more often in a geometric procession. That is, the most priority ones needs to be double the one that is immediately below it. So if we lay out turns this way, we can reduce the distance of SL0. For example, this is the most notable case, and that's because we get this distance to a quarter of the original value while keeping the same distance in SL3, which is the least priority one. So, okay, that's theory, but we want to be able to implement this solution in hardware. So we need to store in the device the arbitration table, which is basically the number of entries times the entry width. And in the case of this example is half a kilobit. Now for each port, we do need to have registers, because each port, as I have said, has to track which entry is the prevalent now and for how long, how many fleets you can send until running out of your quantum. And that is in this case 24 bits. If we sum that, we have the total bits for one port HCA. Ideally, we would want to, let's say in switches or multi-port HCAs, to share the same arbitration table. And the space requirements for this solution scale linearly with the parameters that we have just exposed. So just to give a graphical show of this, we can see that no matter how much we scale those parameters, the cost is indeed linear. Okay, so for the performance evaluation of our experiments, we have used simulation. We have used our Sauron simulator, and we have experimented in a 512 nodes parallel generalized fat tree topology with deterministic DMOD K routing using random synthetic traffic. We have tested 3 arbitration table configurations with 5 service levels each. The first one, we called it fair, and it distributes the bandwidth evenly among every service level. The next one, we call it step. It distributes the bandwidth in a linearly increasing manner among the several service levels. And the last one, we call it 2 powers, and it distributes the bandwidth among the service levels in an exponential way. So quality of service is not only about about bandwidth, it's also about latency. And we want to explore what happens with network latency and packet latency, that is, from the injection of the packet and from the generation of the packet. So our targets, let's say what happens with the fair table. Our target is to have the bandwidth distributed evenly. And this is what happens with the default round robin arbitration. And well, it happens to distribute the bandwidth evenly because round robin itself is it distributes the bandwidth evenly on a packet basis. So that's our solution, and that's what we expect. However, if we look at the latencies, we can see that the network latency has really changed, and we have privileged the SL0 and so on against the less prevalent queues. Now, regarding packet latency, we can see that it may seem a little anomalous, but we have to take into account that packet latency is also caused by packets stalled on buffers. So those service levels generate less traffic, so packets are stuck on buffers for not for shorter periods of time. However, we can see that service level 0 suffers the most from degradation due to having only one entry or one of those small chunks of quantum when we laid out the turns. Now, if we look at the step table configuration, our target is to have is to reach the throughput as I have laid out with the color dots. However, we do not reach that value. Why? Because the round robin scheduling does not guarantee that you pass the 20% mark, and the SL0 to SL2 only pass because the other service levels do not generate as much traffic. I mean, the SL3 and SL4 they just get what they generate regardless of their assignation. However, with our solution, we do get the target results, and if we compare that to our target ones, we can see that that is accurate. Now, we can see that in network latency, our increasing the latency when the service levels are less prevalent becomes even more evident. And in packet latency, we also have the same behavior as before, because of also the ratio between the generated traffic and the bandwidth assignment for each service level. However, if we look at the 2 powers configuration, we want to target the bandwidth assignment as the table configuration expressed. We will not get it for the same reason as the step table. However, we do get it with our solution. And if we compare that to our target throughput values, we can see that we have reached it. Now, regarding latency, it is evident that it has an effect on network latency. In fact, each value is halved whenever a service level is more prevalent to another. And if we look at packet latency, we managed to invert the tendency that we have seen before, because in this case, the ratio between generation and bandwidth assignment is the same among all the service levels. And even then, we managed to squeeze a little bit of latency for service level 0 compared to service level 1, and so on and so on. So what we get from this is that our solution provides a correct and accurate bandwidth allocation, and our latency tuning technique is indeed effective. Our solution to provide our information to provide the solution has been, we think, insightful about the requirements for our implementation in hardware, and we believe it's actually feasible to have a sort of hardware implementation or a prototype of our solution. And how we would like to improve and build upon our solution would be to experiment with realistic traffic patterns, because, well, this is synthetic traffic, and we would like to know how this behaves with real applications. And we could even have further improvements on our solutions in terms of accuracy, especially with if exploring more cases with variable packet size. So that's it for my part. We are a minute early, so I have more time for any of your questions. Thank you.
Thank you so much. Audience, any questions? By the way, Miguel, can you see the Slack chat?
No, sorry, I have not logged into Slack.
Okay, I'm monitoring for you. I don't see questions at this moment. So there's one question from Heshang. He's asking whether this is BXI3 or BXV2.
This is actually BXI3. BXI3 is being developed on this framework of well, I don't want to get too political, but on building European technology to host the future of supercomputing, and that's what we have been working for, and it's evident is present in many projects to build its new interconnection network for this to tackle this issue. So yeah, it's actually BXI3.
Okay, thank you.
You're welcome.
So anyone else? So while we are waiting for some more questions, maybe let me check with you. So did you compare with any state-of-the-art scheduling mechanisms? Can you make some comments on that?
No, we did not. And I mean, this is something that other reviewers have told us to compare with other technologies, but we did not think that we could compare to other technologies because our solution is especially tailored to BXI3. And
Okay.
yeah, I think the novelty of our solution is that there is nothing to compare us with regarding BXI3 because currently, as far as we know, there are no other solutions present.
Okay, I see. Thank you.
You're welcome.
Anyone else? Please feel free to type your questions on the Slack channel so that I can help you. Okay, so one last question maybe from me. What's your future plan? Have you try to evaluate with your solutions with some real applications? Let's say today we heard so many AI workload kind of things. Do you see any potential of utilizing your techniques for those kind of scenarios?
Yes, in fact, we have taken a look at the ML and Horobot traffic patterns that they generate when they train, and we have found that well, even though the network is not always used, there are traffic spikes that really make heavy use of the networks, and that's actually one of the issues we want to tackle, right? That you may have some, let's say, sleeping application that is computing all the time, but suddenly it has to get access to the network, and latency is really a make or break thing when those applications are working. So yeah, actually, we're working in introducing traffic traces from horrible training in our simulator to examine how it works and how it behaves when this happens.
Okay, I see. Thank you. So I think time's is up. So thanks again for your talk, and for audience, please.
You're welcome.
Yeah, I think Slack channel still there, so please feel free to type your questions over there. And Miguel, please check that, and you probably can answer questions offline if there are
Okay.
any. Thank you.